Carnot Principles. Is the Carnot engine the most efficient engine possible? The Carnot engine is just one example of a reversible engine. But is it the most efficient engine possible? We can think of many other engine cycles, both reversible and irreversible. Are any of them more efficient than a Carnot engine? What we are going to show is that the Carnot engine is in fact the most efficient engine possible. We are going to show this by stating what are known as the Carnot Principles. The first Carnot principle says that the efficiency of a reversible heat engine is always greater than that of an irreversible engine operating between the same two temperatures. The second Carnot principle says that the efficiency of all reversible heat engines operating between the same two temperatures are the same. We have over here a heat source at temperature TH and a heat sink at temperature TC. We set up two engines to operate between TH and TC. The first is a reversible engine. The other is an irreversible engine. Both of them are supplied the same amount of heat, QH. We now assume that the irreversible engine is the more efficient one out of the two. The work output from the irreversible engine is Wi, and it is going to be greater than the work output of the reversible engine. So Wi is greater than WR. The irreversible engine rejects heat QCI, and the reversible engine rejects heat QCR. Since the irreversible engine is more efficient, QCI will be less than QCR. Now the reversible engine can be reversed and operated as a refrigerator. We now have a reversible refrigerator instead of the reversible engine. This takes heat QCR from the heat sink, and it rejects heat QH to the heat source. The refrigerator requires work WR to operate, and we can supply this from the irreversible engine. Since the work output of the irreversible engine WI is greater than WR, there's still net work WI minus WR, which is done on the surroundings. The refrigerator is rejecting heat QH to the heat source. The irreversible engine is taking the same amount of heat QH from the heat source. We can therefore connect the refrigerator directly to the engine and eliminate the high temperature reservoir altogether. We can also take the heat QCI, which is rejected by the engine, and supply that directly to the refrigerator. Since QCR is greater than QCI, there's still a net amount of heat, QCR minus QCI, taken from the low temperature reservoir. If we now place a box around this device that we have built, which consists of the refrigerator and the irreversible engine, this device is taking heat QCR minus QCI from a single thermal reservoir, which is the heat sink. It is also doing a net amount of work, Wi minus WR, on the surroundings. Now, this device that we have built is a perpetual motion machine of the second kind, which is taking heat from a single thermal reservoir and doing a net amount of work on the surroundings. We know that this is a violation of the second law of thermodynamics and cannot possibly exist. So we started this analysis by assuming that the irreversible engine is more efficient than the reversible engine. This assumption led us to creating a perpetual motion machine, which we know violates the second law of thermodynamics. We must therefore conclude that the efficiency of a reversible heat engine is always greater than that of an irreversible engine operating between the same two temperatures. This is the first Carnot principle, and this is what allows us to avoid violating the second law of thermodynamics. We can prove the second Carnot principle in exactly the same way that we proved the first. We take two reversible engines and operate them between the temperatures TH and TC. These are reversible engine 1 and reversible engine 2. They both are supplied exactly the same amount of heat, QH. We now assume that reversible engine 2 is more efficient than the reversible engine 1. The work output from this engine, WR2, is therefore greater than the work output, WR1. The heat rejected from the reversible engine 2, which is QC2, is therefore going to be less than the heat rejected by reversible engine 1, which is QC1. We now take the reversible engine 1 and we reverse it so that it operates as a refrigerator. The work required to drive the refrigerator, WR1, can be supplied by the reversible engine 2. WR2 is greater than WR1, so there's still a net amount of work, WR2 minus WR1, which is supplied to the surroundings. We can connect the refrigerator to the engine and eliminate the high temperature reservoir. The heat rejected by the engine is sent directly to the refrigerator. So there's only a net amount, QC1 minus QC2, that is taken from the low temperature reservoir. If we put a box around this device that we have built, which consists of the refrigerator and the reversible engine 2, then this is a device that takes heat QC1 minus QC2 from a single thermal reservoir, and it does a net amount of work, WR2 minus WR1, on the surroundings. We have once again built a perpetual motion machine of the second kind, and we know that this violates the second law of thermodynamics. So in this case, we started off by assuming that one reversible engine is more efficient than another. This assumption again led to the formation of a perpetual motion machine of the second kind, which violates the second law of thermodynamics. Therefore, we must conclude that the efficiencies of all reversible heat engines operating between the same two temperatures are the same. This is the second Carnot principle, and we must assume this to avoid violating the second law of thermodynamics. To summarize, the efficiency of a reversible heat engine is always greater than that of an irreversible engine operating between the same two temperatures. The efficiencies of all reversible heat engines operating between the same two temperatures are the same. A Carnot engine is reversible and is therefore the most efficient engine possible. Any other reversible engine will have an efficiency equal to that of a Carnot engine, not any greater.